All right, welcome back everyone. This is Unit 1, Section 4, or Part 4, video number 4. This will be labeled Part 4D. And we're going to start with slide 21. We're down to slide 20. Start slide 21 and go another about 15 to 20 minutes. All right, so take a moment and read this question, please. All right, when you're done, you're writing down your answers, compare with your neighbor. There is more than one potentially be correct, so. All right, let's go through this one as a group. So we're talking about changing the frequency. And we know the frequency f is equal to 1 over 2L square root of T over mu. Okay, so if I replace a string with a thicker string, what am I changing? Okay, you said we're changing mu, changing the linear density of the string, you are correct. And what are we trying to find in this one? We want to increase the frequency of the lowest frequency. So we're trying to find a way to make F1 have a larger frequency. So if mu is bigger, I'm going to have 1 over a bigger number, which is going to make F1 smaller. So increasing the string with a thicker frequency will not make it have a higher frequency. Okay, what else if we increase the tension? So if T gets bigger, what happens? As T gets bigger, then F1 gets bigger. If F1 gets bigger, our frequency is bigger. So B is definitely an answer. What does C do? You pluck the string harder, what happens? That just changes the amplitude, right? Is there any part in this problem of amplitude? No. Amplitude does not change the frequency. So C does not matter. How about D? We double the length of our string, what happens? Well, if we double L, then this is going to be a 1 over 2, which means our frequency is going to be half as large, which is going to drive our point of increasing it to be a smaller value. So that means D is not true. That means the only answer on this one is going to be B. And sure enough, our answer is B. Okay, let's look at another example. Okay, take a moment and read this question real quick. Take a moment, figure out what you know and don't know, and figure out what they are asking us to find. When we do that, I'm going to get this set up on the document camera. So the $1 million question, what are we trying to find? And if you set the tension in the string, you win. All right, so we're looking for the tension. If you want to know what is the tension in the string, what do we know? Well, it tells us that it plays the string A we still know A at a frequency of 110 hertz. This is going to be our fundamental frequency, F1. So F1 is going to be 110 hertz. Okay, it tells us between two fixed points of 0.68 or 0.64 meters apart. So that's going to be L. Okay, and it tells us our total mass. The total mass is going to be 2.86 grams. Okay. So this is a problem they're talking about, things like frequency, length, tension. So we're looking for the tensions. We want something that relates our tension to our frequency. And we've had one we worked very recently that says F1 is equal to 1 over 2L square root of T over mu. Okay, so here we have our L, we have our F, we have our T, and we're just looking for this mu. And we can find mu, right? We know mu is mass per length. We know all of that stuff. Okay, so let's go ahead and start working this one out. We're gonna solve it for T. So first thing we're gonna do is we're gonna get the square root part here by itself. Okay, so we're going to have F1 times 2L is equal to the square root of T over mu. Then we got a free T from the inside the square root. So to do that, we have to square both sides. So we're going to get F1 2L squared is equal to T over mu. And we have to solve for T. I'm going to go ahead and switch the sides of the T. So T is equal to F1 2L squared times mu. Now we know everything but mu. So we're going to have to find mu. So we said mu was equal to M over L. And so we know M is in grams. Do we want to leave M in grams? No, we want to convert it. What are we converting M to? If you said kilograms, you are correct. So we're going to have 2.86 grams is going to be let's do 1 kilogram on top, and 10 to the negative 3 grams on the bottom. I did that backwards. Let's do that again. M is equal to 2.86 grams. We want to go to kilograms. We want grams on the bottom, we want kilograms on top. So 1,000 grams in a kilogram. Let's do it that way. Which gives us 2.86 times 10 to the negative 3 kilograms. There we go. So we're going to get 2.86 times 10 to the third kilograms divided by L, which is 0.64 meters. Put that into your calculator, which I actually don't have worked out in my notes, so I'm going to do the same thing you are. Which is going to give us 4,469 kilograms per meter. Except that, let's try that again, negative 3. That number sounds really huge. Let's try that number. That looks better. Should be a very small number. That's still kilograms per meter. So we can write this in scientific notation of being 4.4 times 10 to the negative 3 kilograms per meter. All right. So let's go ahead and put that in for T now. T, we said was F1, which was 100 hertz, 110 hertz. Big parentheses down, times 2 times our length of 0.64 meters. That whole quantity is going to be squared times our mu of 4.4 times 10 to the negative 3 kilograms per meter. Okay, now you're going to throw this whole mess in your calculator. And when you do, according to my notes, you should have 88.6 meters. Okay, any questions on this one? Oh, right. Well, we're going to pause here and reset the video and do another part. Oh my God.